next step is to figure out how to apply this to modeling. So we can create models of the universe using our momentum and our changes in momentum, along with our positions and changes in positions. The general form for this is going to follow our normal change model from before. The final momentum is going to be equal to the initial momentum plus the impulse, which is F delta t. Notice these are all vectors, and the directionality of these vectors is very important in considering changes and in predicting future locations and other future speeds. The other thing to note is that since these are vectors, we can and should treat each of the individual momentum components in terms of each of the individual force components. So the x direction momentum is equal to the initial x direction momentum plus the x direction forces times the time intervals, and similar for y and z components. When you have multiple forces, so in this formula here, delta P1 represents the effect, the impulse caused by the first force, plus the impulse caused by the second force, plus the impulse caused by the third force, and so forth. There are connections between velocity and momentum, and we can look at the momentum change, and we can convert that into a velocity change by dividing by the mass in every term. And if you wanted to include relativity, you would actually, of course, divide by gamma m. But we can work that another time in another way. So our change in velocity can be related to our force acting over our displacement. This, of course, assumes a constant mass, which is not necessarily the case, but if one calculates the change in momentum first and then applies that mass as an instantaneous value, you can find at least an approximation of the speeds and velocities and changes in velocities as time continues. The next thing we do here is we look at the relationship between velocity and force and also position. So by doing a little bit of algebraic magic here, we find that the average speed over a given time interval is given by this term, Vix plus half F net x divided by m times delta t, and then plug that into our position formula so that we have our final position is our initial position plus the average speed times the time. And then when we make this substitution in here for the average speed, we find that our final position is equal to our initial position plus the initial velocity times the change in time plus this half F net x divided by m t squared term here. As an aside, a common formulation of Newton's second law is in terms of acceleration, rate of change of velocity. Force to mass. So you can see that plugged in here very nicely. This is a different kind of model. It's another change model, but it's a different kind of change model because it's the ratio of cause, action, to resistance to change. So another, or a definition of mass, is the resistance to change in motion, inertia, which is Newton's first law. This assumes a constant F, or at least an average F. And I think the distinction here is kind of important in the sense that the force is the cause of the change, the mass is the resistance to change, and the acceleration is the result. You will frequently see this written as F equals ma, which, while it's algebraically true, is misleading, because the force is not the result, the force is the cause. The acceleration is the result, the acceleration is the change. And I think this is very suggestive of that fact, whereas F equals ma tends to obscure that fact. And it's a thing I know from experience is that people do tend